Hi, Advanced Algebra 2. Welcome to our Concept 22 notes. In these notes, we're going to look at inverse functions. Now, up until this point, you have worked with inverse operations. That's operations in math that undo each other, like addition and subtraction, multiplication and division. Well, an inverse function are equations that will undo each other. I know that's kind of a strange concept. We're going to start with a little exploration, which is what we do sometimes. So if you're watching these in the video, you're going to do this on your own. So each pair of functions that you can see in the box on my screen or on the video screen, and then also in your notes packet, those are inverses of each other. So that means they undo the math of each other. So in the first function, if we look at the pair in example A, if I plug in a number for x and get out a number for f of x and take that number and put it into my g function and plug it in, I will be right back to the original number that I started with. That's what inverse functions do. So what I want to explore is what inverse functions look like when you graph them together. And that will help us understand what's going on with these inverse functions. So you can graph these pairs, and we're going to graph them as pairs. Either on your graphing calculator, or you can go to Desmos.com. I'm going to show you on the video these functions graphed on Desmos, and we're going to look at the characteristics of the graph. And then we'll get into exactly what inverses are and how to find an inverse function, and then I think you'll understand more about the graphs. So let's look at pair A. We have a linear function f of x and another linear function g of x. So 4x plus 3 and then x minus 3 over 4. So I'm going to pull up a Desmos screen and show you those two functions graphed together. All right, hopefully you're looking at your graph as well, either on your graphing calculator or on Desmos. So notice I have the first function f of x in red and the second function in blue. So if we notice, you can see where they cross. Now I'm going to show you the line y equals x. So notice when I do that, that looks like a line of reflection for those graphs of these two inverse functions. And so what is happening is that in one of our graphs, so for example in the red line, we have the point 0, 3. And then if you look on the blue graph, we have the point 3, 0. So literally the x and the y points are interchanging, and that enables the graph to be reflected over that diagonal line y equals x. Now look at your notes, back at your notes, and look at the second pair of functions in B. So notice in B we have our first function f of x is a cubic function, and then our second function g of x is a cube root function. So go ahead and graph those, and then let's take a look at the graphs together. I'm going to graph mine on Desmos. All right, here you see my functions. Well, at least I have the first one, the cubic function, graphed on Desmos. So that's a familiar shape to us. A lot of the cubic functions that we graphed were a little more curvy. But now let me graph this cube root function. There, and I think you can see how it is symmetrical over that line y equals x. So literally we have the point 0, 2, it's 0, 1 on our cubic function, and that means that we will have the inverse, the 0.10 on our cube root function. So it's just a property of inverses that they have points that are where the x and the y values interchange. Now I'm going to go right to our next pair of functions, and you can graph them. You can always pause the video and graph them. So here we have a square root and then a quadratic function. And you know, if you were solving an equation, that those operations undo each other. Notice that our domain of our quadratic function is limited. And so that's just to emphasize, when we limit the domain of that it is the inverse of our square root function. And there's the line y equals x, so you can see how they are a reflection. And then finally, I'm going to pull up pair D. And again, this is just a little exploration. So these are called rational functions. We're going to study them later in the semester. Our first one and our second one there. And then if we show that line of reflection, and we could do the same thing with looking at points. So we have the point on the blue function, 0, -1, and we can find the point that's symmetrical across. All right, I'm going to backtrack a little bit because I think my video paused, but we have these two functions that are inverses, and you can see that they are symmetrical or reflecting over the line y equals x. All right, so back to our notes. Let's just make a point to say that the graphs of inverses, these are actually equations that will undo the math of each other. They reflect over that line y equals x. Look at exploration 2. So now you're going to be given a graph of a function, and then you need to create the graph of its inverse. And so this is just a fun little graphing thing where you're just going to reflect it over that line xy. So you can do that just by, eyeballing it. You can also find a point. So I look at graph A and I notice the point 0, 1. And so I could graph the point, 0, -1. I could graph the point -1, 0. If they'll let me. There we go. And so there is the line. That would be the graph of the inverse of the function. You can do the same thing with B. So just reflect some of those points and then that curve. Same thing with C. Now you worked in it or saw an example like this when you were graphing. So this is a cubic function. And then our graph of the inverse would be a cube root function. And then finally, just reflecting. All right, now we're going to get into the notes that talk about really more about inverse equations and functions. So just a final note that the graphs of inverses, they reflect over the line y equals x, and to create them you can reflect points. You can also find points on the original function and just reverse the coordinates. So the x becomes the y value and the y becomes the x. All right, as we step into the idea of inverse functions, we need to talk about another definition, something called a one-to-one function. This is taking the definition of just a function one step further. So remember, the definition of a function is for each input there's exactly one output. So with a one-to-one function, however, each x value corresponds to one y value, and each y value corresponds to only one x value. So this is what a one-to-one function is. Now, just like test for regular functions, if you remember, you can do the vertical line test. We're going to talk about two tests to determine if a function is one-to-one. That means for each x there's exactly one y, and then for each y there's exactly one x. So the first test is the horizontal line test. So if any horizontal line intersects the graph in no more than one point, then the function is one-to-one. The second test is to look at the graph of the function that's in question. As you look at it left to right, examining the domain, if it increases over its entire domain or decreases over its entire domain, then it is one-to-one, meaning it doesn't switch directions. Now, why do we care about if a function is one-to-one? Because if a function is one-to-one, then its inverse function is one-to-one. So this is a picture of how inverse functions work, how they undo each other. So we have the number 10, we're plugging it into that f function, so 8 times 10 plus 5, that's 85. Now the inverse function, g, we take 85 and plug it in, so we subtract 5 and divide by 8, and look, we're back to our original value. Now here's how you can find inverse functions. Up until now, I've just been showing you pairs of ones, but you can actually find the inverse of a function. So the first method would be if you were just given a set of points, like inputs and outputs. We would first make sure that the function is 1 to 1. So for each x there's one y, and for each y there's one x. And then you just simply switch the inputs and the outputs. Now method number 2 would be if you were given the function in equation form. Then we have to go through some steps to find the inverse equation. So step 1 would be you switch the input and output variables. You just interchange x and y in the equation. You solve for the new y, and then you replace that with inverse function notation, which is f to the negative 1x, but you read that inverse function of x. So let's try a couple of these. So we're going to find the inverse of the function. So we're given the function in equation form, f of x equals 2x plus 3, but then we are given a set of inputs and outputs, points. So to find the inverse, we are simply going to do the inverse of these points. So we scan to make sure for each x there's one y, and for each y there's one x, and that's true. We see no repeats. And then I'm going to create a new table, and this is my inverse table. So I'm simply going to interchange my x and y values. So the original function we have the point negative 2, 1, and in the inverse function we have the point negative 1, 2. The original function we have the point negative 1, 1, and then in our inverse function we have the point 1, negative 1, etc. Okay, so that's method 1. Now we're going to use method 2 in examples B, C, and D where we're given equations. So the first thing we're going to do is we're going to write this in an equation form, and it's a line, and a line is a 1-to-1 function. Then I'm going to interchange my x and y's. So look what I did. I literally have written x where y was and y where x was. Now I'm going to solve for my new y. So I'll do that by adding 1 and then dividing by 3. So my inverse function, that means the equation that will undo my original one, is x plus 1 over 3. And then I'm going to write that using inverse function notation. So the inverse function of f of x is x plus 1 over 3. Let's try another one. So let's start by writing in an equation form. It's an equation of a line, which is a 1-to-1 function. Let's interchange our x's and y's and then solve for our new y. Now let's write that using our inverse function notation. So this equation will literally undo the math of our original function, f of x equals 2x. One more, okay? So let's write it in equation form. You're going to interchange your x's and y's, your inputs and outputs, and then solve for your new y. So add 2, multiply everything by 3. So 3x plus 6. And now let's write that using our inverse function notation. All right, there is some practice, and now let's keep going on our study of inverse functions. We're going to do one more example to finish off part 1 of the notes. So we're going to find the inverse function of a quadratic, the inverse of a quadratic function that has a limited domain. Now we limit the domain, and then that allows this function to be 1-to-1. So if I do a quick sketch of this, oh, it's rough, okay, x, y. So this is just the parent quadratic, but it's only where my x values are positive. So it is simply this part of my parabola. And then if I did my horizontal line test, I would see that it's 1-to-1. That ensures me that the inverse that I find will be a function. So let's start by writing in equation form and interchanging our x's and y's. Now I'm going to take the square root of both sides, so y will equal the square root of x. All right, now I need to go back to my original function and figure out what my range is. And so you can see that the curve is where all the y values are greater than or equal to 0. Now what happens with an inverse function is that the domain and the range of the inverse function literally just interchange with the domain and range of the original. So for my domain of my inverse function, I look at the range. So it'll be greater than or equal to 0. And then for my range, I look at the domain, greater than or equal to 0. Why is it important that the domain is limited? Otherwise, our original function would not be 1-to-1, and then that means that our inverse would not be a function. Now let's look at the graph of the original function and its inverse. So again, rough sketch. Here's a graph of the inverse function. So it's y equals the square root of x. And now there is that original function. So you can see that it has the quality that we noticed early on in the notes, that these are reflections over that line y equals x. All right, this concludes our part 1 notes of inverse functions. So I will do some more examples with you for part 2 of concept 22.